Hello everyone. In this presentation, I will talk about my PhD dissertation titled AI Power System Scientific Defense for High Confidence Cyberphysical Systems, Modeling, Analyze, and Design. This talk includes 5 parts. In part 1, I will talk about AI Power System Scientific Defense for High Confidence CPS. Part 2 provides an overview of my contribution. In part 3, I will zoom into one representative work, and in part 4, I will zoom out to briefly talk about 3 additional works. And finally, part 5 provide our vision and future works. So let's start with part 1. CPS are smart systems that include cyber, physical, and computational components, which has been widely applied in applications such as autonomous driving, nuclear power plants, and medical surgery. Since all those tasks are life critical, we require the system to behave in good fashion that are well understood, predictable, justifiable, trusted, or equivalently in high confidence that can resist both natural disasters and malicious attacks. Despite the efforts from researchers and enterprise defense teams, we have witnessed a growing number of cyber incidents over the past 15 years with growing damage in the unit of billion dollars. Moreover, we have witnessed cyber physical attacks such as the famous Stuxnet that distracted Iran nuclear power plants. Therefore, the unsatisfying stat core leads us to develop the next generation defense against these CPS threats. So our solution is DAISY, defense through AI-powered system scientific methods, where we managed to enable the 6 transformation of security paradigms to solve the associated challenges in the current security landscape. We'll go them one by one. So first, we develop quantitative security paradigms rather than empirical defense that rely on empirical rules to address the challenge of security metrics. Second, technical defense cannot protect human, so we develop social technical solutions to address human-related attacks. Third, as attacks and users are strategic, defense is not a single agent optimization, but a multi-agent problem. First, as perfect security is impossible or too costly to achieve, we need to extend security to the concept of resilience. And fifth, despite the piecemeal design of CPS, we need a built-in rather than add-on security. And finally, we need to change the defense from reactive to proactive to overcome the defender's natural disadvantages. Now we go to the part 2 to review our work in the thesis that achieved this 6th dimension of transformation. So in one sentence, the contribution of the thesis is to help the defender to mitigate 3 classes of vulnerability related to posture, information, and human. So first, for posture-related vulnerability, we focus on dynamic protection of critical infrastructures such as power and transportation. And this part contains 2 works. In chapter 3, we focus on prevention and response of cascading failure in large-scale critical infrastructure network that are independent and interconnected. In chapter 4, we focus on time-sensitive attack response in nuclear power plants. For information-related vulnerability, we focus on deception that contain 2 parts. So the first part develop counter-deception technology to undermine attackers' information advantages. While the second part, on the contrary, designs defensive deception to establish information advantage for the defender. So for counter deception, we aim to remove the rock of the defender so that he can see the truth. Well, for defensive deception, we aim to set up the screen for the defender to deceive the attacker. So for the counter deception part, we focus on zero trust defense against advanced persistent threats, APTs, and in this chapter 5. And APTs are a class of stealthy and persistent attack that contains multiple stages to achieve the compromise. We further investigate deception among intelligent robots in chapter 6 for scenarios of cooperating, foraging, and touring. For defensive deception in part 3, we develop cognitive honeypots for lateral movement mitigation in chapter 7. And the key insight of this work is that static security is not true security. So if you see this figure, every time step is secure. However, if you see from the entire timeline, it's not secure because there could be time spatial attack paths if the attackers can persistently stay in the system. In chapter 8, we investigate optimal honeypot engagement policies to obtain high-level threat intelligence such as attack tools and attack goals, rather than low-level indicators of compromise such as IP address and hash value that are less costly for the attacker to change them to evade the detection. So for the human-related vulnerability, we classify them into the acquired vulnerability and innate vulnerability. Acquired vulnerability are caused by lack of incentives and security awareness, which can be mitigated through security training and incentives. On the other hand, the innate vulnerability are caused by bounded attention and rationality, which is hard to change because this is human nature. So for acquired vulnerability, we focus on insider threats mitigation, and we will talk about these two chapters in detail just a few slides later. For innate vulnerability, we focus on the one that relate to attention. So the first work, we develop human assistive technology called AVERT for phishing prevention. Well, in chapter 12, we develop a framework called randoms against information DOS attacks. So this first work deal with passive attentional attacks because they aim to remain stealthy and evade attention. So this kind of attacks exploit, but does not change human attention pattern. And for the second work, the attacker aimed to increase the human cognitive load by generating a lot of faint attacks. For example, in this figure, attackers can intentionally trigger a lot of lures so that a human fails to identify the real attacks. So we refer to this new type of attacks as IDOS, information denial of service attacks, as an analogy to DOS attack. So here is an overview of our problem level contribution where these 10 works solve the 3 types of vulnerabilities to achieve the 6 transformation that we have shown in slides before. So now we are ready to zoom into one representative work in chapter 3 to illustrate how we achieve this 6 transformation of security paradigms. The work aimed to address the problem of insider threats, which refer to vulnerability and risk caused by the misbehavior of the trusted but not trustworthy insiders. As shown is in the figure on the right from the Verizon data breach report in 2021. In the past 5 years, insider threats has caused around 40% of breaches with significant damages, which shows the necessity and urgency to solve the problem. So existing solutions are mostly empirical, such as awareness training, relieving workload pressure, reward punishment, and audits. And they are difficult to quantify and automate it, as we will meet the problems such as how much reward to provide, how frequent to audit, how much impact are caused by these factors. So in this work, we provide a framework called Zeta that stands for Zero Trust Audit and recommendation with the following 3 advantages. First, Zeta is proactive and affordable because we can reduce non-compliant action by designing insiders' incentives. Second, Zeta provide a non-invasive way because we motivate rather than command an employee to act in an organization's interest. And third, Zeta is quantitative, automated, and transferable. Despite those benefits, designing incentives are challenging. So first, incentives are not directly observable, controllable. Therefore, we need to develop formal design framework to obtain metrics of trust, compliance, and certification. The second, incentive customization is costly for a large population of insiders with varied incentives. Therefore, we need automated design. And the third is incentives not directly observable. Therefore, we need the feedback system that can learn their incentive fastly for timely mitigation. So our framework is complicated. So let's consider the following motivating example instead. There are a population of employees or insiders, which are used interchangeably in this work. They have different incentives to comply with security rules. For example, this guy is amenable and he's glad to follow security rules. This guy is self-interest, he follow rules if they didn't conflict his interest. And this guy is malicious, he doesn't want to follow rules. So the defender in an organization want the insider to follow security rules. So one way to do that is by applying audits to all employees, either by the defender himself or through a third party. So what is an audit scheme? In this example, an audit has three steps. First, check an employee's action, either compliant or not compliant. Then apply a scoring a scheme based on the action. So we can adopt different evaluation schemes, just like different scores we use to grade a student's final exam. It could be pass or fail, could be A, B, C, D, could be a score between 0 to 100. And the third step, we just reward and punish the employee based on his compliance score. So in this example, we consider two different audit schemes based on different scoring systems. Stringent audit here, the score the violation of all rules, while this tolerant one score only the selected rules. So defender can randomly implement an audit scheme from these two options. So we can construct this utility matrix of insiders and defenders to evaluate the impact of different audit schemes. So the VU represent an insider's incentive under different audit schemes and actions. Similarly, we have this VD matrix to represent the defender's security objectives. An insider knows that these two audits have happened with probability 0.3 and 0.6, but he doesn't know which audit scheme is implemented. So now let's ask the question. What action should a rational insider take? Basically, he need to compare how much benefit he can get by implementing these two actions. So if we take action non-compliance, then he obtain 0.28 on average by taking expectation over this probability of audit. And if he take compliant action, he obtain a 0 on average. And because this number is bigger than 0, he will choose non-compliance as his initial compliance status. So since the insider takes this non-compliant action in red, we can compute the expected utility over the probability of this two audit scheme as the metric of innate satisfaction level and the innate security level for the defender and the employees respectively. So this ISEL measures how compliant an employee is. The defender in this work may not be able to design the probability of audit, as the audit may be conducted by the third party or restricted by some regulation rules. So now the question is, how can the defender improve the compliance of the employees? Basically, the compliance here is measured by the security level. So, so we can do that. One way to answer this question is by strategic recommendation. Basically, you can think the audit as a way to threaten insiders to well behave, to be not punished. And the recommendation is a complementary way to make the threat more believable and more effective. So let's see how it works. A recommendation mechanism contains two things. One is the recommendation, either complying or not complying, and a recommendation policy P1, P2. So the recommendation is generated based on the audit scheme. If it's stringent audit, then we recommend this red and blue with probability P1 and 1 minus P1. If this tolerant audit, then recommend the red and blue with probability P2 and 1 minus P2 respectively. So the goal is to design the recommendation policy P1, P2 such that employees are willing to follow all recommendations, and also the defender achieve the optimal security level. So the trustworthy here means that the defender recommend an action and then the employee just follow the recommendation. So let's see how this recommendation can affect an employee's belief and their actions. So first we assign these numbers, and simple computation shows that the red and blue recommendation happen with probability 0.2 and 0.7 respectively. So if the employee received the right recommendation, he knows directly that the audit scheme is the tolerant one because P1 equal to 0. Then based on this posterior belief, he compared these two actions and then choose non-compliance. So he followed the recommendation. If on the other hand, the employee received the blue recommendation, then based on the base rule, his posterior belief is 0.5, 0.5 for these two audit schemes. Then based on the posterior belief, he compared these two actions, and then he found I should choose compliance as his action. So also it's follow the recommendation. So we see that employee follow both recommendations, and now what happens is that he take compliant action with probability 0.72. So if you still remember that without recommendation, his initial compliance status is to always not comply. So now we see that there are actually improvements of compliance under the recommendation scheme. So when we want to formally measure such compliance improvements, so we need the following metrics. First, for the defender, when the insider choose non-compliance and compliance, these two actions, he obtains minus 1 and minus 0.3 respectively, both based on this audit probability. So we know that these two actions happen with probability 0.2 and 0.7. So on average, he obtained minus 0.7184, which is referred to as the acquired security level. On the other hand, for the insiders, when he chooses non-compliance action, he receives 1 on average based on his posterior belief of 0.1. And when he chooses compliance, he has a different posterior belief and obtains 0 on average. Then we average over the probability of these two actions are taken and obtain this acquired certification level of 0.28. So in this example, when we compare innate and acquired security level and certification level, we found that the certification level of the employee remained the same, while the defender security level increased. So that means that there's actually a win-win situation, and we can actually formally prove that it's true. This win-win situation always happens for all the trustworthy recommendations. And by proposing those metrics such as the certification level and the two security level, and also the difference measures how the difference between these two security level measures how persuadable, trainable an employee is. So by proposing this matrix, we're developing a scoring system address the metric challenge that we have proposed. We have identified several slides ago. And we can further generalize our framework to non-binary case and develop convex programming for an automated design, which address these two challenge we have identified. So for the third challenge that incentives are unknown in practice, our solution is to apply feedback that can learn the insiders' incentives based on their behaviors. But we actually managed to do it in a smart way, in a non-traditional way, as we'll be showing in the next few slides. To illustrate how we do that, we first need to provide a geometric characterization of the recommendation policy. So first, this is just copy-paste the slides we have, which have the functional representation on the recommendation policy. We can equivalently represent it in the matrix way, where P1, P1, P2, and P2. Because we have this binary recommendation and they have to sum to be 1, we only have two free variables, P1 and P2. So that means that the entire policy space is actually this square, where P1 and P2 both from 0 to 1. And each point in this square represents a policy. For example, this policy is represented by 0 and 0.4. So now we can transform this figure into this 3D figure where the x and y axis are the same with this two. So under each P1, P2 pair, the defender's security level is different and actually shows in this z-axis. So the point here actually correspond to the optimal security level the defender can have. So we have shown the binary case on the left. We can extend it in two directions. So it's binary x and binary s. So for non-binary all the x in the column, the square become a hypercube of I dimension. And for non-binary recommendation in the row, we have k hypercubes rather than just one hypercube. So remember, the challenge is to mitigate insider threat timely. And a classical solution uses this kind of update evaluate loop and have to search over the entire policy space. Because we have a non-convex surface, it's not very efficient and global optimal is not guaranteed. So for our solution, we managed to use some special structures. So here, instead of learning the entire surface, we only need to know the partition. And for each partition, we can prove that it's actually piecewise linear. And also because the only thing unknown, the partition, is actually because of the unknown incentives. So once the defender knows the partition, he can compute the surface directly as he knows his security objective. And the partition here just means that we this policy sets we aim to find. So now the question becomes, how can we learn the sets and how to learn it fast? We observe two properties that are really useful. First, we show that the side is connected and represent a convex polytope in the hypercube space, just like here. And second, we show that it's sufficient to determine the policy set in each hypercube independently. So that enables us to separate the design. We will briefly illustrate how this property can help us. The separability means that in the case hypercube, remember that we have k hypercube. In the case hypercube, we only need to consider one recommendation as k, rather than all the k recommendations. And the hyper and this sk represents a hyperplane. And in one region, the insider is complying, the other is not. So now we just need to consider this polytope And because of convexity, for this vertex, we only need to learn the vertex to determine this prototype. And moreover, all these vertex are on the edge of this hypercube. So so we only need to learn the vertex to determine the region. And this is in 3D, and we want to illustrate how we learn a vertex in 2D, but it's actually applied to any dimensions. So first, we test whether these four vertex represented, whether they represent a trustworthy recommendation that's shown in blue. And starting from each blue vertex, if the neighboring node is also blue, then we know this all the points on this line are trustworthy recommendation, and there's no additional vertex to determine. But if the neighboring node is red, there is one and only one additional vertex to determine. And we can use binary search to find this point. So we first test the half of these 2 points. And here it's red, so it means that insider doesn't comply with the policy. So now we can test this point, the half of these 2 new points, and repeat until we find the turning point in this blue of this blue circle, and then this is the region we want to find. So our algorithm is efficient. For the worst case, when this blue circle is very near to this to the vertex, we can still guarantee to achieve the accuracy epsilon with a small number of steps. So here we show that it's used less than 7 steps to achieve the accuracy of 0.01. So after we get the vertex representation here, we can use some method to compute the hot plane representation. So for example, if we get the coordinates of this point as 0w, then the line here can be represented by the constraint as follows. And then we just need another coupling constraint saying that P1 and P2 should all belong to 0 to 1. So we formally summarize the result presented in the previous slides in the theorem, which we prove that all 4 of them are hold for all zeta settings. So here's a callback of how this work contributes to the DZ landscape. We have all those metrics and consider a proactive way to mitigate insider threats. Proactive because we use incentive design. And the audit and recommendation provide a social technical solution. And we consider the interaction of insider and the defender as the multi-agent problem. So Zeta focus on information design. We have another work that extend to consider a holistic design of information, reward structure, and different and trust. Moreover, it's consider a holistic design of different type of users. So this extension of holistic design further achieve the dimension of built-in security. So in this extension work, we lay the theoretical foundation for deception design and have these 2 principles. The separation principle says the defender can design reward structure independently without any loss of generality. And the equivalence principle says that the design information and trust is equivalent to design trust when there's no constraints. Okay, so we have finished chapter 3 where we zoom into one representative work. And now in part 4, we zoom out to provide a sketch of 3 additional works. So we have already talked about 9 and 10 in details. Now we just briefly talk about chapter 3. Chapter 3 deals with prevention and response of casting failure. So the first challenge results from large scale and interdependency. To address that, we propose factor Markov game to reduce complexity. So it exploits sparsity and manage to reduce the complexity from exponential to polynomial. It contributes to the holistic design aspect of DZ. To address the second challenge of long-term protection and the limited resources, we develop a dynamic strategy to trade off protection and recovery, which enables resilience. So we apply this method to a case study of NY subway power network to prevent cascading failures. So node here represent a subway station or power substation, and the links represent their interdependency. So the repair policy managed to recover the network in a efficient way. And now we talk about chapter 5. Chapter 5 develop zero trust defense against APTs. And to address the first challenge of stealthy and persistent attacks, we propose a zero trust and behavior-based defense by this dynamic Bayes scheme, DBGS. To address the PBNE computation for DBG, we propose efficient algorithm to exploit country prior, and we further develop a multi-scale computation scheme based on constructive proof in this paper. We have a case study based on TE process to corroborate the design. Now we talk about chapter 11 that focus on phishing prevention. So the challenge here is to enhance users' attention to improve phishing recognition. So for the attention part in red, we laid theoretical foundation to analyze, evaluate, and modify the human attention process in phishing. For the challenge of phishing recognition in blue, we propose adaptive human assistive technology called AVERT that analyze eye tracking and survey data collected based on the NYU undergrads. And we found based on our data sets that our technology can improve the accuracy from 74% to 93% within a small number of turning stages. So the figure on the right illustrates an example of the eye gaze trajectory from our datasets over one phishing email on the XY coordinates. So basically, we expand the trajectory of their eye gaze along the time in this z-axis. So this is how people read the email. We can see some patterns from left to right and then from top to bottom. So now we come to our final parts of future works and visions. We have characterized 5 generations of security paradigms, and here is a brief timeline. For 1G security, there's actually no security, and for 2G, there's a parameter security, and the 3G and 4G security paradigm adopts reactive and proactive security respectively. And finally, we're saying that now in 5G, we should adopt a federated security that incorporates all the technology in the previous 4 generations. And at DZ, our work laid the foundation to 5G security paradigm of federated security by achieving these 6 transformations. So human will be the key problem in 5G SP. To mitigate human-related vulnerability, we have talked about the following 5 ways. They are provide incentive, provide disincentive, disclose information, design assistive technology, and manipulate emotions, beliefs, and perceptions. So our current works focus on these 4, but we will continue exploring more about these 5 aspects to solve human challenges for 5G SP. So when applying all those methods, there's 2 main challenges from data and models. So we can solve data challenge by model-guided learning to develop deep intelligence that contain excessive laws and principles, which will make the method explainable and transferable. The current security challenge in security is that we do not have enough data. and it's also not clear what data should we collect, especially for human-related ones. So the deep intelligence can further help us to collect data efficiently. So secondly, we can solve model challenge by data-driven mechanisms. So we have human system on the left, we have the CPS system on the right. Human take action and then get perception from the CPS. For we will in the vision we will need a system level characterization. That means that on the one hand, we can develop data-driven human assistive mechanisms that are cognitive about human vulnerability and can assist human in correcting their misbehavior adaptively. On the other hand, we also need to better understand human mental process in CPS and develop the theory of security mind. So finally, based on all these 10 works, we have the following 4 aspects of contribution. So first, we develop many models and frameworks for different problems. We have made several theoretical advances and proposed a lot of efficient algorithms to realize the developed technology. Finally, our methods have been applied in many mission-critical applications. And here are 5 takeaway message before I end the presentation. First, security are now in 5G, and that means that 5G solutions are needed for all these 5G security problems. Second, DZ laid the foundation of 5G security paradigm by achieving 6 transformation. Third, DZ achieved 4 dimensions of contributions. And finally, is promising to expand the 5 ways of human factor engineering and address model data challenges for this 5G security paradigm. So hopefully this 4 number of 5645 can help you remember what we have covered in these talks. And the end is the reference, and thank you very much for your attention.